Good afternoon, everybody. We'll continue today transformer. Last time we explained transformer as an ideal device. We just said we assumed no power loss, nothing, just the voltage and the primary side is going to be transferred to the secondary winding. Either it's a step up transformer or a step down, so the voltage on the secondary can be increased or decreased. But everything was ideal, and we got the turns ratio N1 over N2. You can call it A or N. It's equal to V1 over V2, and also we said that it's equal E1 over E2. The difference between the voltage and the EMF, the voltage is the voltage of the source. If you talk about the primary side here, V1. And E1, it's the one across the wine, the primary wine. The same thing here. V2 is the voltage across the terminals of the secondary, and E2 is across the wine. So today we're going to have the practical transformer. We're going to include the power loss and the magnetization effect. First of all, we have windings. So it's very obvious once you have windings, they are made of wire, they have resistance. And the resistance of each winding, if you look for the primary, and you have turns, the number of turns equal to N1. So the resistance of this winding, it depends on the length of the wire, the cross section, and the material made of. Because as you know, the resistance is equal L times rho or divided by sigma A. That's the resistance. So we can get the resistance for both windings. So we ignored it last time. So the resistance of the primary winding, it's called R1. The resistance of the secondary winding is called R2. And measured the ohm. So we're going now to add two resistance. What does it mean? It means if you have current I1, there will be a voltage drop across R1. So E1 will not be equal to V1. So where's E1? That's E1. E1 is the EMF across the primary line. So it means E1 is going to be less than V1 because the current I1 will cause voltage drop across R1. The same thing happens in the secondary side due to the voltage drop across R2, which is the resistance of the secondary wire. There is something else. When you look for the current I1 flowing in the primary winding N1, so this current will produce magnetic field. And the magnetic flux will have two parts. There is one which is flowing through the core. That's the mutual flux. And other flux leakages, phi L1 and phi L1, it's the leakage flux that does not flow in the core and does not link the other winding. It's only linking its own winding in one, and most of this flux in the air, as you see, part in the winding, most of it in the air. So what does it mean? It means, because we know the air has permeability mu naught constant, does not change. So expect that the relationship between the flux and the current will be linear for the flux leakage. But it was not included in our ideal transform model. And how can you calculate the effect of the flux, or how can you represent it? When you have power loss, you can represent it by resistance. What about the leakage? How can you represent it? Always anything connected to power loss, we deal with resistance, and anything deal with magnetic field or magnetic flux, it means we are going to deal with inductance. That's very obvious. So when you look at it, we'll say we know that the inductance in general, we study that in the magnetic circuit, it's equal N phi over I, and also we did something that we can find N squared divided by the reluctance. All right. I'm going to use this formula to study the effect of phi L1. Phi L1 is the flux leakage related to the winding number one or the primary one. So now I can say the inductance of the leakage one will be equal to in which N? The primary in one, and which flux? Not the whole flux, only the flux leakage. L1 and divided by I1. That will give me the inductance of the that relate to the leakage flux, and you can call this one the leakage inductance. So let's just call it name so you know what does it mean. So L in general inductance, but L, small l, that's the leakage inductance. L capital, L small. But you got to, since we wrote one of winding or number one. What's phi L1? It's the flux or the leakage flux related to winding one. And once we found the inductance, which is relate the flux to the current, we can find X, the reactance. How can you find the reactance? We know there is a general formula for the reactance is equal omega L. And omega is equal 2 pi F L. So that's a general expression for any inductive reactance. Accordingly, we can write X. You see, I mean, I'm going to find the reactance corresponding to the inductance L1. So I'll call it the same thing. X L1 will be equal to pi F L1. Just simple as this. So when you look at this circuit, we have two elements: the resistance and the reactance. The resistance represents the resistance of the winding, or the power loss, you can say. The power loss, it will cause power loss in the winding due to the current flowing in it. And XLL1 is going to represent the reactance, and it will represent the voltage drop caused by the flux leakage in winding number one. And the same thing for the other side. So now we have like Z. You can call this one Z1, and you call this one Z2. If you wish, you can call it Z1, and this one, you call it Z2. And if you connect resistance at the load, V2, as we explained last lecture, you can find the equivalent circuit to the primary side and just like one circuit. Okay, but I'm not going to this one now. I mean, we want to understand today in this lecture the practical transformer. Ideal transformer we did last lecture is very useful, because when we start to do analysis or design, it's better to have like a quick way to give you idea. And once you find you are in the right way, then you go ahead and do the details to get precise answer or solution. There is something else. We talk about the voltage drop due to the resistance of the winding and the flux leakage, that leakage here is not connecting both. What about phi M? How can I represent it? There are two phenomena that we didn't include it yet in our practical transformer model. The first one, phi m, which is the mutual flux which flowing through the core, and that's responsible for building the magnetization in the transformer. So how can I represent it? The interesting thing that this flux, the main flux or mutual flux, it's not written here, but let me write just this one, call it phi m. That's the mutual flux. Why I call it mutual flux? Because it's the flux connecting both windings, 1 and 2. Who is responsible for that? How can I represent it in our model? That's one thing. Second thing, if you remember in the previous lecture, we said that because the flux is changing with time. Why changing with time? Because the flux is reduced by the current, and the current reduced by the voltage source, and the voltage source is sinusoidal. So sinusoidal voltage source reduce sinusoidal current source, reduce sinusoidal flux. So the mutual flux phi m, as we explained magnetic circuit, it takes, I mean, it's changing with time. And since it's going to intersect or the core of the transformer, we said that will be like eddy current. If you remember, eddy current will reduce because there's flux changing and there is a conductor, so it'll be EMF, and then it's closed, so it'll be current. That's a loss. How I represent it in our transformer model. And the proof for that, if you have a transformer or adapter, you plug it to the wall, and even you don't put to your mobile or you don't put to anything without connected to any load, it gets hot. Why? It gets hot, and I don't load the transformer because of that. Because the magnetic field built, and it's changing with time, and it's intersecting with the core itself, and producing the eddy current and what we called also the core loss, even if you don't have load to the adapter of the transformer. How can you represent that? And that happened before even you load the transformer. So we can do it. And now we are going to have more elements in the transformer. Let's make it bigger. What you see in front of you here, that's what we did. That's the Z2, you can say, the winding 2, and that's Z1. The branch in the middle has 2 elements when you observe. You got resistance, we call it RC1, and you got reactance called XM1. What are those? XM1, it comes from LM. What does it mean, LM? The mutual inductance. Because I want to find the effect of phi m, something to represent phi m, the mutual flux that's in the core. You can get it, you know, I can use the rule n square divided by the reluctance. If you are at the primary side, winding 1, so you are finding LM1, you divide N1 square by the reluctance R1. And actually the reluctance R1 and R2 be the same because it will be the reluctance of the core. We don't have any air gap. Let me show you what they mean by that. That's phi m, and phi m flowing in the core. So you got to calculate the reluctance of the core. And if you are using N1 square, so you are getting the corresponding inductance or mutual inductance on the primary side. If you are making N2 square divided by the reluctance, it's the same reluctance also, you will get the inductance that represents the mutual inductance on the secondary side. So that's how you can get the inductance, and accordingly, you can get XM1 2 pi F L M1. So that's how you represent the reactance that's responsible for the mutual flux. You got 2 things. You got mutual flux, you got leakage flux. Now they are represented. the leakage flux in the primary side represented by XL1 and the mutual represented by XM1. Just you got to know that from the basic electricity, from basic circuits. Power loss related to resistance. Magnetic field, that's inductance or inductive reactance. Electric field, that will be capacitor. Well, I'm not dealing with capacitor here. Well, what about RC1? RC1, it's a resistance, represent the power loss, even if you don't have load. What is this power loss? It represents the core loss. Before you put load to the transformer, already you get shot. Why get shot? Because I explained the eddy current that's going there. So that will be the resistance RC1 that represents the core loss. So that's related to the mutual flux, and RC1 represent the core loss in the transformer. And there's something important. If you have no load here, so you will have I2 equals 0. If you don't connect load to the transformer, what you get? I2 equals 0. So what's I2 dash? I2 dash, it's the equivalent current, the equivalent secondary current I2 on the primary side. How we do it? By the turns ratio. Let me refresh your memory. We agree that E1 over E2 equal I2 over I1, N1 over N2, and we can call it A, turns ratio. We did that last time. So if you want to find the equivalent of I2, it's not going to be I1, be I2 dash. So how we find I2 dash? Just put I2 dash into I1. That will get the same thing. I2 dash would be equal to I2, right, times N2 over N1, which is 1 over A. So actually, I2 dash is equal I2 divided by A. So if I2 equals 0, so I2 dash is equal 0. So I1 is the current coming from the power supply. So the all current I1 in the primary winding coming from the power supply, it will be equal to I phi 1. It will be only supplying the core loss and building the magnetic field in the core. So that the all I1 would be equal, whole thing like that. That's the, which is, so we'll say at no load, you will have I1 is equal I phi. What's I phi 1? What's I phi 1? That's the one responsible for two parts. One for the core loss, let's make it vector. Core loss, and one for the flux, IM1. Why I write IM1, not IM2? Because I'm in the primary one. Can you do it in the second? Yes, of course, you can find that code. But let's just do it in this one. And you got to remember something. You can plot the phasor diagram of the current. When you look at the voltage here, or E1, if you look at E1, E1 is across XM1 and across RC1 in parallel. So if you have E1 here, so you observe that IC1 will be in the phase with E1. Let me just sketch to you. If you have E1 in this direction, so I and RC1, so IC, when you divide E1 by RC1, you get IC1 in phase, always the current in phase with the resistance. So let's choose different colors. So you have, let's say that this is IC1. And when you look for the other one, XM1, the impedance will be JXM1. And you divide to get IM1, you will say IM1 is equal A1 divided by JXM1. If you assume that this is angle 0, as we did here, doesn't hurt. So J is 90, go up will be minus 90. So it will be equal minus J E1 over Xm. That's all magnitude. So it means the direction of the current IM1 has magnitude E1 over Xm, and the direction is minus 90. So you can do it like that. That will be IM1 perpendicular. And that's obvious because I'm in the inductor. And the resultant will give you the total current, which is here I phi 1. So if you want to find the resultant, you can just do that, make the parallelogram, and that will be I phi 1, which is this one, which is I1 at the same time at no load, because you don't have I2 dash here. So that will be the current. Obviously, that will be the angle between the E1 and I1, the current in the primary. It's lagging, of course. Yeah. That's if you like, I mean, to make analyze. Well, now let's just go more practical, because that's the experiment you're going to do it next week, transformer. How can you, it's not practical if I have the transformer to destroy it, get the winding, and get the length of the wire, and to calculate the resistance. Or yes, if it's given, if the information given to me, I can use it, but I want to do experiment in the lab. So I can do the following. I want to calculate what's the value of RC, XM, R1, X1, R2, X2. If there is a way using voltmeter, wattmeter, ammeter, and then I can find, of course, yes. So to do that in transformer, you have to, you can say you have two tests. One test called no load test, but sometimes they call it open circuit test. And you have the second one, short circuit test. Short circuit test, it means that you go to the secondary and make short and you get the measurement. I'm going to explain it in detail. But these two tests, it will help you to get the all parameters that you need. When you do the no load test, you will get this branch, RC1 and XM1. It will give you something represent the core loss and the reactance responsible for building the mutual flux in that. That's no load test. And usually we do it in the, if this is the low voltage side and this is the high voltage side, usually you do it like that. We open circuit the high voltage. What do you mean high voltage? And the low voltage side. Let's say I have a transformer, said 100 to 1000. 100 to 1000, mean 100 volt to 1000 volts. So 100 side, that's the low voltage side. And the 1000, it's called high voltage side. So I'm not going to use primary or secondary because maybe you have step up, step down transformer. So I'm going to say now low voltage side and high, and you know what, why we're saying that. So when you do the open circuit test, you are going to have open loop in high voltage side and put your measurement tool in the low voltage side. What the measuring instrument you're going to use? A voltmeter, ammeter, wattmeter. You want to measure the voltage, the current, and the power. That's the two measurements you're going to use to find R and C and X, M. When you want to find R1, X1, R2, X2, you are going to do short circuit test. When you do short circuit test, you are going to short circuit the low voltage side and put your measuring tool at the high voltage side. That's what you're going to do. That's practically what they do. In the lab, not to confuse you, because I want you once you use the measuring instrument on one side, I don't want you waste your time to disconnect your circuit again and you connect it again. So to make it easy, I let it everything you are going to put the old measuring instrument because you have in both sides. But the old thing I do, I'm not going to apply a full voltage on the primary side. I will just use small portion. Why I'm doing that? Because I'm afraid to get high current in the winding, especially in the short circuit. I'm not worried about no load tests. When you have short circuit test, it means R equals 0. You get the max current. So I don't want to destroy the transformer. That's why they change the side. I'm not going to change the side, but I'm not going to apply the normal voltage. If the normal voltage is 100 volts, I'm going to apply 20% out of it, and the Beazer side. Just why I'm telling you that, because when you do it, you don't say, for example, like XM2, you change the sides when you do the tests, but I'm just doing that for your comfort, how to do it in the right way. Can you do it practically? Yes, of course. You just don't apply the rate voltage, that's all. So now we are going to do the test for both with data, because they're going to have the when I upload the lab experiment, I'm going to give you like a numerical example you solve before you go, so you know what you're going to do. But we want to understand today and Friday lecture, we want to understand really very well how we implement it. Let me show you. When you do the equivalent circuit, I showed you here, that's exactly what's happened. You are going to add this branch and observe that you have R1 and X1 here, and you have on the other side R2, X2. But when you analyze the circuit, it's always better to move everything to one side. So I'm going to move R2 and XL2 to primary winding. So that's what I did here. I moved, so it becomes R2 dash and XL2 dash. And you have here R1 and X1, and you got this branch in the model. And that's I mean, like make it easy. And we can simplify it more. Here you go. That's what we got. Because the current I phi is small. It's really small. So it's like, I mean, that's the current I1, and that's, we call it I2 dash, and that's I1, and that's I phi. So when you say if I1, let's say, is equal 10 amp, I mean, I phi will be equal to 0.5 amp. And then I2 dash would be equal to 9.5 amp. Just let's make something simple like that. So they found out, since that's the case, when you have branch in the middle, it make the circuit analysis complicated. It will make it complicated. And all the engineers try to find something simple, but does not affect the final result. So I said, okay, we're going to take the whole branch and just we're going to move it here. So we can add R1 to R2, XL1 to XL2, so it will make life easy. And that's what they did. So when you see that in any textbook on how you solve the problem, that's, I mean, everybody agree about it, all electrical engineers. And even if you want to make something very simple, since this is very small, why you just don't take it out and just leave in the end the R equivalent and X equivalent, and the life will be good and simple, and you still get good results. Yes. Well, so why did you explain all the things, Abraham? Because it depends on the application and depends on the transformer. Imagine if you are working with Georgia Power and you got the substation power transformer. We are working with 11 kilovolts, working with megawatt. You are not going to ignore it. You got to use it. So it depends on what type of transformer you use. That's why I'm going to explain. So you got to know. This is, I mean, that is good if you want to include it, and that's good if you don't want to include it. And the decision depends on the transformer type and the application. Saying that, now let's just go to the test. How you make the no load test and the short circuit test. That's exactly like what you're going to do in the lab. Let's say that in the open circuit test, we have to test. Open circuit test, I'll make it OC. And you're going to have voltmeter. And you're going to have a meter to measure the amp. And you're going to have wattmeter to measure the power. And you have, okay, let's just try to be organized a little bit. And you got two scenarios. You got open circuit test and short circuit test. And that sometimes we call it no load. Open circuit test, it was done on the high voltage side. That was open. And they put the all instrument on the all measurement on the low voltage side. So I'll sketch you something fast here for the open loop. So that was open. All right. That's the high voltage side, and that's the low voltage side. And then they put the instrument here. They put their meter, voltmeter, and also they have the wattmeter at the same time. What they measure here on the low voltage side, that's open circuit here. It was 220 volts, 2.5 amp, and the power 100 watts. That's for the open circuit test. And for short circuit test, they did something different. What they did here, you have, that's the low voltage, and that's the high voltage side. Here, the low voltage side was shorted. So they make short circuit here. And then they start to measure the current and the voltage other side. So B150 volt, 4.55 amp, 215 watt. Now let's just, before that, I supposed to tell you what the information of the transformer, the test is performed on. It's the data of this transformer when they read the plate on the transformer. It was like single phase. They write like that, single phase, 10 kilo volt amp, 220 volt, 60 hertz. That's the information that when you there are of course more, but that's the electrical information. You'll find it on the nameplate of transformer. They add, of course, the normal temperatures, the cooling, the thing. I'm not going to go all detail. I'm just now going for the important information that you need to know so you can make your analysis, your test. It's single phase, it's 10 kilo volt amp. And when they tell you 2,200, the 220 volt means that's the normal or rated voltage that is supposed to use. You can use less than that, but you don't exceed that. It means that the high voltage side is 2,200 volt, and the other side will be 220 volt. And you can get from that the turns ratio. Is it the exact one? No, it's the approximation, of course, because that's the voltage and E is less than, but it's acceptable. That's what the engineering they do. So the first thing I'm going to do, I will get the right information. The right information, I can say that the turns ratio A, which is equal N1 over N2, if I consider this is 1 and this is 2, and that's the order given on the nameplate, I will say it's 2,200 divided by 220, cancel will be like 10 to 1. So A is equal 10 to 1. You can write it like that, write equal 10. A, 1 to 2. All right. There is something else I mean, I'm telling you what the information you can get. That's single phase and 10 kilo volt amp. So it means that I can get the rated current of each side. What do you mean by that? Well, I know that 10 kilo volt amp, that's equal to voltage in single phase times current. If we are using the voltage rating on this transformer, V1 rated value, so the corresponding current I1 will be the rated value. So because I like to know what the current, appropriate current that I suppose not to exceed it. So I can get it from all this information. So I'll say 10 times 1,000 equal V1, which is equal to 200 times I1 rated value. So in this case, I1 is equal 10 times 1,000 divided by 2,200. Well, I wonder if you have calculator. Yeah. Okay. All right. If somebody can calculate, just you will get the N for the I1. That will be the rated value of the current. If you want to make protection, you get fuse, then you get it related to this current. The same way you can get I2. It will be just 10 times 1,000 and divided by 220. You get the rated current. All right, have a calculator. All right, that will be 2,020, and then you have 100 over 22, right? That will be 5. That's right. 4.55. You can say. All right, and this one will be, of course, bigger 10 times, right? Without calculation, be 5.5, because the ratio is 10. And here the voltage decrease, the M increase, follows the opposite works here. So I got the values of the transformer that's important to know before yes.
10 kVA, you're supposed to have one more zero.
10 kVA.
Yeah, where it says 10 kVA equals V1 rated times I1 rated, then you put the next line is 10 times 1,000, should be 10,000.
It's 10 times 1,000.
Okay.
So that's the rated current. Now let's go and use the information of open circuit test. You did this. You did the test. That's open circuit. You put the instrument on the low volt side, and let's just find how can you get what you're going to get RC and XM. To do that, I'd like to just sketch the circuit here to make sure what I'm doing. This is the branch I'm supposed to get from open circuit test. You will have like inductor, and that's XM1. I want to find it. And I have RC1. And let's now see what's happening. In open circuit test, what we got here, 220 voltage. And we got 2.5 amp. And we got 100 watts. So how can this information help me? All right. So I will say 2.5 amp going here. That's what I measure for the M. That's I1. All right. And we know that I2 dash is equal 0 as we explained. So the all current will be, that's the no load current, right? All of it going to the magnetization. And the voltage is equal to 220. So that's 220 volts. I'm trying to translate what did I measure and put it in my equivalent circuit so it will help me to find the values for the parameters. All right. Now, when you say 100 watt, is it related to RC1 or XM1? RC1 to the resistance, right? So I will say this one responsible for consuming 100 watts. Now I can find things. Well, what you can find. You have 220 volt, it's across the resistance and across the reactance. And they have the M, 2.5. So what can you get? How can you get RC1, for example? What's the relation between RC1? It's given the power. Power PC1 is equal 100 watts. And what's power? You know power. It's equal I square R, V square over R, many things, right? You have the voltage. You have the resistance. You don't have the resistance, but I'm saying you have the voltage. So I'll say it's equal V1 square over RC1, right? The all 220 volt across RC1. Accordingly, I can find RC1. RC1 will be equal to V1 square over VC1. So in the lab, when you get the measurement of the power and you put the voltage, you know the value, you just directly, you can calculate RC1. So RC1 in this example will be equal to 220 voltage squared divided by the power 100 watt. And you get RC1. I think I calculated it's equal 4 point, no, sorry, equal 484 ohm. That's the first thing. All right. More than that, I can find, it's not required, but I can find IC1 if you like. How can we find IC1? I divided the voltage by the resistance, it's just current. So I will say I'm going to find IC1. That's for fun, not just, I don't need it, maybe. So IC1 is equal V1 over RC1. So I have 220 voltage divided by RC1, 484 ohm. So I get 0.45 amp. All right. I'm interested to find XM. I'm interested to find the all parameters of the transformer. How can you find XM? You have the voltage only. Of course, the current here should be equal to IM1, but you don't know IM1. But what do you know? You know IC1, and you know the total current, 2.5. Can you find IM1? Yes, because both, some both. But there is, some mistakes sometimes happen. Sometimes when students solve the problem, they think they are going to subtract algebraically. It means that 2.5 minus 0.45, then they get IM. No, because I explained just 5 minutes ago that the current IM and ICD are perpendicular. Because there is one in the inductor, one in the resistor, as you studied in circuit 2. So the I total, when you have R and X, the I total will be equal to IC squared plus IM squared. So here, you know that that's IC1. You got it 0.45. M1, you don't know it, but you know the total because you measured in the lab by the ammeter and it was 2.5. So what you call this one? We call it I5, 2.5. And so you will say I5, which is I1 also, they are equal, square is equal to IC1 square plus IM1 square. That's IC1, that's IM1. It make a figure. So if you want to find IM1, so we'll say I1 square minus IC1 square root. I1 in this case was 2.5 amp squared, and IC1 we got 0.45 square root, and then you get IM. That's about 2.46 amp. That will be the magnetizing current. So you got IM1. Once you got IM1, if you go back here, IM1, you can get XM. Why? Because you divide the voltage by IM1, it gives you XM1. So XM1 equal to V1 divided by IM1. If you like to make a one formula just not to go through the things, you can write it like that. I like when I was student just to put one formula because I don't like to go through the steps. I would say it's equal V1 measured. IM1 I didn't measure in the lab, but I measured I1, and IC1 was calculated here, right? It will be a little bit complicated, but if you like, you make the steps. But if you want to make one formula, will be IM1 the square root of I1 squared measured in the lab, and IC1 I got it by dividing V1 over RC1. If you want, that's another way to calculate. Anyway, but this is a mean symbol, of course. You got XM1. Let's find how you get it. XM1 is equal V1 220 voltage, and IM1 we got it 2.46. So it will be equal to 89.4 ohm. Good. So that's the XM. Now I can make the branch here, the inductance. It is equal J89.4, and RC1 I just got it. It was equal to 484 ohm. And that's all what you need from this test to get this branch. Just simple as it is. Now, what's left? That I should make the short circuit test. Short circuit test, as we explained, you are going to, how many minutes do we have? 4 minutes. Okay. Short circuit test, that's what I'm going to do. That's the transformer. And we agree that's the low voltage side. And that's the high voltage side. We make short circuit on the low voltage side. And of course, as you know, there is a resistance here. And there is a resistance here. And there is the branch, if we are working on the side, the branch will be another there. And you apply the voltage here. So when you put the oil instrument on this side, on the high voltage side, you are going to measure voltage, current, power. Same thing. The measurement when you did the test, it was 150 voltage, 4.55 amp, 215 watt. The measurement of V2 and I2 and P2, it will help you to get the value of R2 or equivalent, the equivalent resistance, but on the secondary side, because you put the measurement here, you are going to put, if just, let me do that. You put your ammeter here, and voltmeter, and wattmeter. So that's what we're going to measure. And what you are measuring, only the resistance and the inductance. Remember that if you are going to refer everything to the secondary or to the high voltage side, the circuit will be like that. That's R equivalent to, and that's X equivalent to. R equivalent to, that is equal R2 plus R1 dash. And X equivalent to will be X2 plus X1 dash. You are measuring the equivalent, but on the side. So this side has its own resistance R2, and the other resistance on the primary side reflected, because you are finding the old instrument on the secondary side. So if you are going to, if you know the voltage here V2, and you know the current I2, what you get if you divide V2 by I2, Z2. What's Z2? All this Z equivalent to is equal R equivalent to plus JX equivalent to. So if you divided V2 over I2, your measurement you have, which is 150 voltage divided by 4.55, you get in ohm. Only you get the magnitude, by the way, because on the angle, the magnitude. If we do that, you'll find is equal 32.97 ohm. That's the Z equivalent for the old transformer on the secondary side. Now you want to find how much R, how much X. You go to the power, as we did exactly. The power always related to the resistance. So the power that you have, 215. What is power? 215. How can you calculate the power? Well, power is equal to I squared. Now I'm not going to use V. Why? Because R and X, they are in series, connected in series. The other branch was in parallel. I don't have a choice. So the I2 square times R equivalent to. Do you have the I2? Yes. The measurement of the ammeter, the magnitude, 4.55. So 4.55 square and times R equivalent. I don't know it. It will give me 215. From this equation, I find R equivalent to. That will be equal to 10.4 ohm. Now you have R equivalent and you have Z equivalent. What you get? X. You know how you get X? You have the triangle, impedance triangle. That's R equivalent to, that's X equivalent to, that's Z equivalent to. You have R equivalent to is equal to 10.4, and X equivalent, you don't know it yet. Z equivalent, we're gonna 32.97. So how you find X equivalent? X equivalent to is equal square root Z equivalent to square minus R equivalent to square. And all the values we have it. 32.97 square minus R equivalent 10.4 square. Then you find X equivalent 31.3 ohm. You got the X equivalent and R equivalent of the transformer, the total. What's left is nothing, because I mean, I have the equivalent circuit of the no load on the elementary and the primary one. Well, take the Z equivalent to and transfer it by multiplying N1 over N2 square, reflect impedance. Then you have the whole model of the transformer, practical model of the transformer, using the no load test and short load test, getting the all parameter without counting the turns, without measuring the wire, just by using measurement instrument. And that's the experiment we're going to do next week. You'll do the calculation. I prepared the thing for you, and I test by myself. You'll do the calculation, you'll find you understand very well, and then you will do the simulation, and then you'll do the connection.